In this video, you will learn how to create LEGO Mindstorm's line follower robot and implement PID algorithm. You can use the driving-based LEGO Mindstorms model with the color sensor attached to the front of the robot like this. Now, we want to control the robot to follow the line. The color sensor will read the value of the reflected light intensity and send it to the controller. The controller will then convert it to percent from 0 to 100. After that, the controller will calculate how fast each of the motor must run. Black has a reflected light intensity of 0%, while white has 100%. If you want the robot to move between the black and white lines, the desired light intensity must be 50%. The difference between the desired value and the actual light sensor value is the error. Our task is to minimize the error by controlling the motor speed. We need the controller to convert the error to a suitable motor speed and minimize the error while running. PID controller uses the present, past, and possible future errors to calculate the appropriate motor speed. Each error, together with its constant, contribute to the speed of the motors. If the controller has all the three branches, it's called a PID controller. If one or two branches are missing, then the controller will be named using the first letter of the remaining branches. For example, a PI controller. The proportional line follower works this way. If the robot detects the reflected light intensity greater than 50%, it will apply more power to the right motor. If the value is lesser, it will apply more power to the left motor. This way, the robot will try to follow the line between the black and white colors. This is the proportional line follower pseudocode. The first line defines the Kp, also known as the proportional constant. The positive or negative sign of the proportional constant determines if the robot will follow the black line from the left or the right side. The second line defines the setpoint constant, which is the value of the desired light intensity. It is the average value of the reflected light intensity of white and black colors. Then we have a loop in which the light sensor value is read. The error is calculated by subtracting the light value from the set point. Then, the steering value is calculated by multiplying the proportional constant to the error. Now we will explain how to implement proportional line follower algorithm in LEGO Mindstorm's brick programming language. To simplify the code, we move the proportional steering value calculation code into a separate block named getP, where the error is multiplied by the input parameter and the resulting value is returned. The proportional line follower program consists of the main loop where the light sensor value is read and calculated the error. Then, the proportional constant is provided for getP block and the result from the getP block is passed to the motor block steering input. Here's the proportional line follower in action. In our case, the proportional constant is set to 1. You might need to adjust the proportional constant of your robot. Take into consideration that the light sensor readings may change if the light in the room changes. Testing the robot during the day with good light conditions might give good results, but testing the robot in the evening might fail. In our case, the motor speed is 50, which is half of the maximum value. Increasing the speed makes the robot wobble and it can slow down the forward movement of the robot, and sometimes the robot fails to follow the line. The integral part of the controller accumulates the error over time. It helps the controller fix small errors and makes the robot turn smoother. The integral code is added in the bold text. Ki is the integral constant. Less code in the cycle leads to faster cycle iterations, and the integral constant should be smaller. Otherwise, the controller will accumulate more than the actual error. The sign of the integral constant matches the sign of the proportional constant. At the beginning, the integral variable is set to 0, and in the loop, the error is added to the integral. Then, the value of the integral constant multiplied by the integral is used to calculate the steering value. To simplify the LEGO Mindstorm's programming language code, we move the integral steering value calculation code to a separate block named getI. In the block getI, the error is accumulated in the variable named integral. Then, the integral variable is multiplied by the input parameter and the resulting value is returned. The proportional integral line follower program calculates the steering value by summing the returned values from the blocks getP and getI. The integral part reduces the wobbling of the robot, and the robot can finish the track a few seconds faster. If you connect the robot to the computer using Bluetooth and run the program, you can drag the mouse cursor over the variables to see the actual values. Here is the demonstration of the actual value received from the GetI block. Usually, the impact of the GetP block on the steering value will be bigger than the impact of the GetI block. If the block GetI returns very big values, then probably the integral constant you have chosen is too big. The derivative part of the controller can potentially fix the predicted future error. The bold text is added code of the derivative part. KD is a derivative constant. Its sign should match the sign of the proportional constant, and its value should be significantly bigger than the integral constant. New variable named last error is defined, and its value is set to 0. In the loop, the last error is subtracted from the current error to calculate the variable named derivative. Then, the value of the derivative constant is multiplied by the derivative, and the result is used to calculate the steering value. At the end of the loop, the last error variable is set to be equal to the current error. To simplify the code, we created a custom block named sum, which can sum 3 numbers, and we created custom block named getD to calculate the steering value of the derivative part. In the block getD, the last error is subtracted from the error, and the result is multiplied by the input parameter. Then, the resulting value is returned. The PID line follower program calculates the steering value by summing the returned values from the blocks getP, getI, and getD. To better understand the role of the derivative part, we suggest finding the minimal possible proportional constant without integral and derivative parts, so that the robot can still follow the line. Then, decrease the proportional constant and set the derivative constant to some value and check if the prediction of the future error can make the robot follow the line. Usually, our derivative constant is bigger than the proportional constant, and the getD block shows significant impact on the steering value only in sharp turns. Sometimes, the black color might not be 100% black and the white color might not be 100% white. This means that the average of the reflected light intensity between the black and white colors might not be 50%. Therefore, the motors will spin in different speeds than they should in the perfect situation. This problem can be fixed by using 2 light sensors. The bold text marks the changes needed for the line follower robot with 2 light sensors. This code takes the reflected light intensity from one sensor and compares it to the reflected light intensity of the other light sensor. There is no need for the set point constant to compare the reflected light intensity. The solution is more stable and less prone to failure. The PID line follower program is modified by adding the second light sensor block. Now, the error is calculated as the difference between the 2 light sensor readings. Here is the demonstration of the actual value received from the getD block. The line follower robot with 2 light sensors is more stable, and its speed is increased to 95% of the maximum allowed speed. The previous line follower version with 1 light sensor was stable with only 60% of the maximum allowed speed. Similarly, the line follower robot with 4 light sensors can be made. You just need to change the error calculation algorithm. Each sensor is given its own priority constant. Corner sensors has higher weight values than the middle sensors. Good luck in building your own line follower robots.